Welcome to Chapter 2, Lesson 2-2, Identifying Functions from Graphical Patterns. So our objective for this lesson is, given the graph of a function, know whether the function is exponential, power, quadratic, or linear, and find the particular equation algebraically. So in other words, we're going to find whether a given function is either of the four functions listed, and of course we are going to solve the equations algebraically. So let's start with linear and constant functions. So what are linear and constant functions? During our discussion on lesson 1, we have introduced to you what a linear function is all about, but that is by taking points and plotting those points on a Cartesian coordinate system with y and x as our axis. And here on this lesson, we are going to go deeper into the details of the linear and constant functions. So a linear function has a form like y is equal to ax plus b. Example, we have y is equal to 3x plus 2. So you would know for sure, and first and foremost, when you see a certain function, that it is linear because of this x. See, if you see an x and it doesn't have an exponent which is greater than 1, in this case our x is a variable with exponent of 1. So in this case, our example would be literally equated to y is equal to 3x1 plus 2. So this is what you have to understand. When you see an equation or a function like this, okay, and when you see that the x is raised to the first power, or x raised to 1 specifically, then you are certain that that is a linear function. But what is a linear function really? A parent function has a linear function rather has the parent function y is equal to x. So this is the most basic of the linear functions. And the equation of the parent function y is equal to x is here, as you can see it. And later on I will show you how to graph the most basic function. The general equation of a linear function is defined in terms of y is equal to ax plus b. So y is equal to ax plus b. Now let us investigate what I drew to you as an example. So that is y is equal to 3x plus 2. Our a here is equal to 3, and our b is equal to 2. Therefore, we have the form y is equal to ax plus b. So notice our example. And this example has a graph which is essentially like this. So it has this graph. Okay? Now a transform function is, of course, when we are talking about transform function, we are talking about transformations. And when we do have transformations, we have either a vertical dilation or a horizontal dilation or a translation, which is either vertical or in the y part of your function, or horizontal or on the x part of your function. So in this case, our example is y is equal to negative 0.7x plus 6. Notice that this transformation has a dilation. So we have a dilation on the on the y-axis. Why? Because we have negative 0.7x, and we have a negative on the front or behind the 0.7x, and we also have a vertical translation, which is 6. And what does 6 to the right means? You have a plus 6. It's a vertical translation, 6 units upwards. And what does the negative means? The negative means that it is dilated, or a reflection across the x-axis. It's a vertical what do you call this? A vertical reflection across the x-axis, right? So notice that the graph is somewhat inverted. It was flipped. Unlike these two functions here, we're in the positive part, and they have an increasing value when x is taken from the origin going to this. So from x is equal to 0 to x is equal to a to x is equal to b until there, and also here. So look at how the transformation is being noticed. Okay? Well, the general equation is sometimes referred to as there is another word for this, and some call it as slope intercept form. Why is slope intercept form? Because A is considered as the slope. So our A here, the A here is actually the slope. And B here is the y-intercept. Okay, it's the y-intercept. Meaning that it touches your equation or your function, your function touches the y-axis. So this is, in this case, this is your y-intercept. And we have just to determine the slope, okay, which is, in this example, our slope is 3. On the other hand, the transform function is sometimes called as, this is sometimes called as the point slope form. So point slope, okay, it doesn't, the space doesn't contain it, so I will just write the dash here, and then point slope form. So this form here is sometimes called as the point slope form. Why point slope form? Because we have the slope, and our slope is, of course, our A. Okay, this is our slope. And our point is actually the point x1, y1. So we have random points, but the point taken here is point x1, y1. So it could be any point, okay? So x1, y1. Okay, so that is an introduction to the linear and constant functions. Now let us go to graphing those functions realistically in terms of graphical patterns. So first we begin with y is equal to x. Okay, let's begin with y is equal to x. Okay, as usual, I'm drawing a table for you guys to see in reality that I am getting points for x and y, and those points will determine my points that will be plotted in order to get the accurate graph for y is equal to x, and to show you that the graph will end something like that. Okay, so I think that's enough. We have enough space for our x values. Our independent values are the x values, and our dependent values are the y values. So we start with a negative integer, let's say -3. You could choose any points, okay? But for the sake of normalizing, okay, I'm getting positive and negative values which are balanced in a way to connect all of them, and then you could see that your x values is from 3 to 3, which means that they are 3 units away from the origin. So there we go. We have our y is equal to x function. So if our x is equal to -3, then our y definitely is also equal to -3. The same is true when our x is equal to -2. Our y is equal to -2, and so on and so forth. So you could see that the pattern, the transformation, and the graph of y is equal to x defined by these points that I took randomly, but of course in a balanced manner, is like that. So let us have grids now. So as you can see, we have enough grid lines to cover all of the points. So let us start with our first point, 3, -3. So let's say one grid line is equal to 1 unit. So that's 1, 2, 3, 1, 2, 3. So that's -3, -3. So it should be here. And then just what do you call this? Just following the direction of these points will lead you to a somewhat linear pattern. So it's like that. Okay? And then we are now ready to connect all of the points. Let's see how this fare. So let's add the points. And I'm going to connect it. Okay, so now I have my, and let me take out the grid lines. So now I have my y is equal to x. That's so thick. Okay, so this is the function f of x, or y is equal to x. Okay, now this function y is equal to x has a certain slope which is increasing and positive. It's positive if it goes like that. Okay, so this is increasing also because, as you notice, as your x goes further from here, your y goes up. Am I correct? Now it goes here, the same pattern could be said. Now this is strictly increasing because in all directions, as you can see, the values of your x and y are strictly increasing in both directions. So it goes to the positive x and your y goes to positive y, and it is increasing. Am I correct? So this one is increasing. The slope is increasing. Okay, increasing, at the same time it is positive. Okay, so now we take a look with its general form. So this is our most basic form, y is equal to x. Now let us take a look when going through the general form, y is equal to ax plus b. In our case, our a here is 3 and our b is 2. So let us also get or create a table. So let's create a table, guys. I don't like one with fields. Okay, so let us create a table. Okay, And I'm going to, of course, as a standard, I'm going to make a table for you. Okay? So we have enough room for our x values and our y values. Okay. Now we have the independent values x, and we have our dependent values y. So if my y is, let me, what do you call, compress it from -2 to +2. Okay? There's no specific reason for compressing it, just for the sake of comfort. So you can do whatever you want. You can limit it from -2 to 2, or you can expand it from -5 to 5. It doesn't matter as long as you are comfortable with what you are doing. But of course, when you are really on the, what do you call this, on a situation wherein you have to manage your time, then make your table for x and y values a little bit compressed, like what I'm doing right now. So it's from -2 to 2. So let us have our y value when our x is -2. So our y value here would be 3 times -2, that's -6, plus 2. So we have +4. Or rather, -4. If we have 3 times -1 for x, plus 2, that would be -1. If it is 0, then we have 2. If it's 1, then we have 5. And if it is 2, then we have 8. So as you can see, the y values are increasing in terms of the difference between the y values. So y1 to y2 has a difference of +3, and 2 to -1 is +3 also, and so on and so forth. Now let us make use of our grid lines again. So as you can see, they are perfectly, the lines y and x axis are perfectly fit for the grid lines. So now we have to plot all of the points here. We have -2 and -4. That would be -2 and -4. So we have 1, 2, and 1, 2, 3, 4. So it would be here. We have -1 and -1. So it would be here. We have 0 and 2. So it would be here. We have 1 and 5. So where is 1 and where is 5? It is 1, 2, 3, 4, 5, 0. Okay, I think I made a mistake here. It should be here. And 1, 2, 3, 4, 5. So 1 and 5 is here. Okay, we don't really need to graph the 2, 8 because we already know the pattern through our 4 points. So it is reflected in the 4 points already. So now we want to graph the function itself, and this graphing will give us a straight line also. So getting rid of the grid lines will give us this graph, okay? And this graph is our function y. Y is equal to 3x plus 2. And our slope is 3. And what do we say about the slope? What is the definition of a slope, by the way? Slope is the change in y over the change in x. Am I correct? Or it is the rise over run, because we are taking the difference between the y values and the x values, the consecutive y values and the consecutive x values. So let us say, for example, and we need the help of the grid lines. So let us say we have this one, and I think I over took it. So I think I'm going to need these points. Okay. So now, what do we want to get here? Let us count our x, or delta x. So our delta x here, delta just means a change, okay? So don't be confused by the word delta. When you see this symbol delta x, it means it's a change. So in this case, change in x. In this case, our change in x, delta x, is here. So what is the change in x here? It's positive 1. It's positive 1, right? Why? Because this is point, what is this point? This is point 1, 2, and this is point 0, 2. So your x goes to the right by positive 1 unit. So it moves to the right at a unit of 1. And then it goes up. So upwards, we have 1 from here. Okay, you count from here, 1, 2, 3. So that's why your delta y, let us have another color for this one. I don't like the indigo again. So let's do like this. Delta y, that's a ay, is equal to 3. And slope is rise over run. That means delta y over delta x. So we have 3 over 1. So that gives us 3. Okay? So that's how they found the slope. Okay? So this is the graph of your y is equal to 3x plus 2. The slope is 3, and we have the y-intercept at 2. This is our y-intercept, as I have mentioned to you earlier. This is the y-intercept. And what does y-intercept means? The y-intercept crosses your y-axis at that point, that which is part of the line that crosses the y-axis. So in this case, what crossed the y-axis is actually this point. And this point is, what is this point? It's 0, 2. Therefore, the y-intercept is 2. This is the y-intercept. When your y-intercept is when x is equal to 0 and y has a certain value. Okay. Now what can we say about the slope of this function, 3x plus 2? We could see that this is also, with respect to the first example, okay, our slope is also positive and increasing. So positive, increasing, or increasingly positive, or those terms, whatever you call it, you could call it increasing and positive, or positive increasing, whichever. And the slope is taken as a change of 3 to the y over a run of 1 to the right. So that is the function 3x plus 2. How about we now investigate the third function, y is equal to 0.7 negative 0.7x plus 6. So using the normal details that we do, the steps that we do, so we begin with creating our independent and our dependent values for x and y. And the same values, so we could take from x is equal to negative 2 up to 2. And you can just neglect the other 2 or the other 4 boxes. So if your x is equal to negative 2 in this equation, then substituting it substituting the x value to the x here will give us negative 0.7. Let us make use of our calculator at this point. Where is our calculator? We need your calculator. Okay. So we have 0.7 or negative 0.7 times 2 will give us 1.4. So it's positive because your x is negative, and we also have a negative part here. So the result will be positive. Am I correct? Okay, so that's 1.4 plus 6 will give you 7.4. Let's go to the x value of negative 1. So that's 0.7 times negative 1. It's positive 0.7 plus 6. That will give us 6.7. And if x is equal to 0, we will have 6.0 or just 6. If it is 1, then 6 minus 0.7, that will give us 5.3. And if it is 2, that will give us 6 minus 1.4, so that will give us 4.6. Am I correct? So 6 minus 1.4. 6 minus 1.4 is equal to 4.6. So I am correct. Okay. Now we have to plot using the grid lines again. Our grid lines are our ultimate savior in this kind of situation. So we define our x and y axis. So this is our x, and this is our y, and we plot the points now. So I'm taking this 1 unit here as 2. So let me adjust this thing first. Okay. So every 1 unit that you see here would be accommodated to a scale of 2. And on here, on the x, oh, okay. I think I messed up my x and y axis. So this is supposed to be the y axis. So this is our y and this is our x. Okay, so all the units that you see on the x-axis are normal. They are by 1 unit. But on the y-axis, they are adjusted to scales of 2. Okay, so we plot the points now. We have negative 2 and 7.4, so that is somewhat... Okay, this is somewhat... negative 2 and 7.4, it's somewhat here. So here, let us say at this point. Okay, and let us take our last value or last pair of point as 2, 4.6. So 2 and 4.6. It should be somewhere here. Okay. Now let us just take those 2 points, because your geometry says that at least 2 points determine a line. So we don't need to, actually we could plot all of the remaining points, especially the points in between x equals negative 2 and x is equal to 2. But for accuracy and relatedly, okay, if you have 2 points, then you could already determine a line. So I'm making it as a short, what do you call this? A short illustration. So this will be the graph. Okay, I'm taking the grids now. I'm taking the grids out now. So this is my function. Y is equal to negative 0.7x plus 6. Okay, and how do the slope now fare with those of the 2 lines that we did? we could see that our slope now is negative, right? Our A is negative 0.7, so it's negative. And in this case, the trend of your slope, and of course the graph is decreasing, and it is negative. It's going down. Your x goes down as your y goes down. So this is negative and decreasing. Understood? And what else can you say about this graph? In terms of dilations, this graph is dilated, reflected across the x-axis. It is a vertical reflection across the x-axis. We flip the original function y is equal to x, and then we move it 6 units to the upwards, okay, and then made a reflection across the x-axis. So that's how it worked.